Hello, welcome to the Fireside Chat for April. For those of you that are new to our Design of Experiments MOOC and the course that we run through Coursera, I run this monthly Fireside Chat with a guest speaker, and we try to explore topics that might be of interest to people that are taking the MOOC, and just people that have a general interest in experimental design. Uh, we always leave some time at the end of the guest presentation for Q&A, and this is a terrific time for you to ask any kind of question that you would like. You could ask a question about the topic that the guest has spoken about. You could ask something about any of the material that's covered in the Coursera courses. Or if you have a specific situation that you're dealing with that you want to ask a question about, we'll try to address that. If you're on Coursera, we post these fireside chat recordings to the courses, and they can be found in the resources tab of your course. Quick reminder: don't have your mics on, keep them muted, and keep your cameras off during the session so that we don't have any disturbances. I know when I do my office hours at home, barking dogs would sometimes sort of interrupt the proceedings. We don't need that. If you want to submit a question to either me or our guest, please do this using the chat function on the Zoom menu. You don't need to wait until the Q&A starts to submit your question. You can start putting it in at any point during the hour that we're together. If your question doesn't get answered during this time, I'll respond to it in Coursera for those of you that are enrolled in the MOOC. Our guest today is Professor Jon Stallrich, who is an associate professor and director of the PhD program for the Department of Statistics at North Carolina State. He earned his PhD in statistics from Virginia Tech. So like me, he's a fellow Hokie. Go Hokies. His research interests include design and analysis of screening experiments, computer experiments, online controlled experiments, functional data analysis, and variable selection. And I'm really pleased that Jon could take time out of his busy schedule to give us a presentation today.
All right, that took so long for it to kick back on. All right, I'm here. Thanks for having me, Doug. I've done this
Jon,
once before and it
it's a
was fun.
pleasure to have you.
Thank you. Yeah, I've done this once before. And actually what I'm presenting today was a follow-up of what I did previously. So yeah, I guess let's just get right on into it. Let me share my screen. Can you see my screen okay?
I've got it.
Great. So yeah, today I'll be presenting about what I call powerful foldover designs. So if you already know about a foldover design, it's mainly known as a way of generating a screening experiment so that your main effect estimators are orthogonal to any second order effects. But what myself and others have kind of discovered is that these are even more powerful than we originally thought, that there's even more that they can do. And that's what sort of the main thing I'm going to be talking about today. If you don't know what foldover designs are, that's fine. I'll give an introduction to it. So the types of problems I'll be talking about are screening experiments where we have M factors that we can manipulate. And there's an assumption that not all of them are really that important for driving some responses variation. Like we commonly do, I'll assume that factors are either numeric with settings standardized between plus or minus one, or two-level categorical factors which only take on those two values. So when we talk about a design, we're really talking about this sort of matrix where each row is describing the settings for each of the factors. So I was developing this alongside working with some people in biomolecular and chemical engineering department here, where they asked, I have 8 factors that I'm trying to optimize for making ethylene from ethane. That is the extent of my knowledge. I'm not an engineer. But that's the gist of what they were trying to do. They said they only have, even though the factors are numeric, they just focused on the 2 extreme values. And so that's 256 possible rows for the design. And I couldn't tell them to do all of them. anyone that's taken a design course know that you shouldn't do that anyway. But it takes 2 months for them to do 20 runs. So they needed, some sophistication with that. So we want to, just like with any experiment, we want to choose our design so that it optimizes some analysis performance. Well, I need to know how I'm going to analyze my data to be able to do that. And so we're going to go into this assuming the settings have been chosen so that this sort of typical response surface methodology model is probably the most complicated model that we would want. So it has these main effects, these bilinear interactions, and then these potential quadratic effects. So that means that we have, if we wanted to fit this full model, we would have this many possible coefficients that we would need to estimate. And so in the context of our ethylene experiment, they don't care about quadratic effects. And so there is up to this many effects that they would want to estimate, but that's 37 is a lot more than 20. And so how am I going to be able to estimate or understand this model if I can't even estimate all the effects? And so the common approach is that we use these effect principles that have come from decades of people doing these types of experiments, and we partition the model into two separate pieces. We've got what we call the main effect model right here, which is just the intercept and the linear main effects. And then the second order part of the model, which is comprised of the interactions and the quadratic effects. And these effect principles, three of them that are important are effect hierarchy, which is saying that most of the responses variation is driven by the main effects. And so these effect sizes tend to be larger than the second order effects. Sparsity is really key here. This tells us that I know there's up to this many effects that could be in the model, but relatively speaking, only a few of them are really going to be active or important. And so that gives me hope that I will be able to find the true model using fewer runs and not being able to estimate all of the effects. And then the final one, which has always been difficult to explain and understand, is talking about the relationship between the second order effects and the linear effects. It says basically you want to think of the second order effects as being children of the first order effects. And so a second order effect can't really exist without some of the parents existing in the first order effects, which means if you can determine that some of these main effects are not important, that tells you that you can automatically eliminate some of the second order effects from consideration. So this kind of all of these sort of combined is what allows us to do an analysis with fewer runs than possible effects. So what we're trying to do is we're trying to come up with a small n design. We don't want to do more runs than we need to. And our analysis is going to be a two-stage approach that really embraces these effect principles. So the stage one model is we're just going to fit the main effect model, which means we're actively ignoring what could be some important second order effects. And we'll just do simple t-tests for screening. I'll show you in a minute. We're actually doing confidence intervals, but there's an equivalence between that. So here's our main effect estimators, and here's the variance of those estimators. And then the stage two model is we'll take what we learn about the main effects to subset which second order effects that we need to consider. And we could do some sort of model selection technique like all subsets with BIC or something like that. And so we want to find a design that optimizes the statistical performance of both stages if possible, but we're really going to focus more on optimizing performance of stage one, because doing that well can have a lot of positive implications on the analysis for stage two because of that effect heredity principle. So like I said, an equivalent way of doing a t-test is to calculate confidence intervals for all of our main effects and to check whether zero's in the interval or not. It's the exact same thing. So here's that equation of an interval. We want to think of it as being made up of four pieces. We've got our estimate. We've got our critical value, which depends on these degrees of freedom, which I define down here. We've got the square root of our estimator for variance. And then we have this piece here, which I call the design variance. It's a part of the variance that only depends on the X1 matrix. So if you told your piece of software to fit just a main effect model, it's going to spit out an estimate for sigma squared using this matrix equation here. And the degrees of freedom is going to be n minus the rank of x1, which should be n plus 1. And so the idea is that factor j is going to be active, like I said before, if it does not contain 0. Now, for this to be a good approach, we need to think about what are we asking of the confidence interval. So this is just sort of the definition of a confidence interval about coverage. But the idea is that um, this idea of coverage connects to testing because is what tells us we get a type 1 error rate of alpha for the truly inactive effects. But for this to work, for this to be statistically valid, we need two properties. We need unbiased estimators of the main effects, and we need an unbiased estimator for the variance. The other thing that we want is for our margins of errors to be small. We want our intervals to be properly calibrated where they need to be, and we also want them to be tight. And this has implications on our power for detecting effects that are actually active. So what do we need to minimize this margin of error? Well, we want to try to make everything in here, which are positive numbers, all of those as close to zero as possible. So we would like to have large degrees of freedom, if possible, but keeping in mind that this critical value does have a lower bound of the standard normal critical value. So you can only decrease it by so much. There's a diminishing return, which I'll talk about later. And we also want to minimize the individual design variances if possible. So let's talk about all these different things that we're trying to do. Traditional optimal designs, they mainly focus on just trying to minimize the design variances. And when you're doing this, you're kind of implicitly assuming that you already know what sigma squared is, and that you would be doing inference using standard normal intervals, which we don't really know what sigma squared is. That's actually a big part of this talk, which I'll go into more detail in a minute. And so one thing is that it's known that these design variances for the setup I gave, they have a lower bound of 1 over n. And actually, you can find designs that have this lower bound. These are these strength 2 orthogonal arrays or orthogonal main effect plans, whichever you want to call them, that are found all throughout Doug's textbooks. But the problem is that they only exist when your run size is a multiple of 4. Sorry for all the complicated math. It just means that n is a multiple of 4. So 4, 8, 12, so on and so forth. So there's lots of run sizes where that's not going to be met. So remember, one thing that we want is for our estimators to be unbiased, but you can show that they are potentially biased by this amount here, where we have the thing that we want plus this extra piece, which depends on properties of our x1 and x2 matrix and the unknown beta 2 vector that we have. So we call this the alias matrix. And what always was really exciting to me about design is that I might not know what beta 2 is, but if I have an idea of what terms I might add in x2, I could be very clever and find a design that makes this alias matrix 0 by making these two matrices orthogonal to each other, which has always been really fascinating to me, and that's going to be a key part actually of a foldover design. Now we have this other part where we want to make sure we have an unbiased estimator for variance, and we also want to have large degrees of freedom if possible. This estimator also is going to be biased if we're not careful. And in fact, there's nothing we can really do about this bias. We can't make it go away. The only way to make it go away is actually a bad strategy, which would completely confound the second order effects with the first order effects. So you don't want to do that. So what's the consequence then of using this biased estimator? Well, how is it biased? This is going to be positive, so it's going to be an inflated estimator, which means my margins of error are going to be bigger than I want. And the consequence of that is that my type 1 error rates are actually going to be smaller than alpha, which seems okay, but it can lead to a massive decrease in power, which is not okay at all. So one thing that you can do to fix this is to do this other thing that I call a pre-selection variance estimator, meaning you can estimate variance that isn't dependent on the model that you're fitting. And all you need to do this is if you really believe that this second order model is the largest possible model, then all you just need to make sure is that the rank of x is less than n, which seems like a bad idea at first, but for the purposes of estimating variance, it's actually a really good strategy to do. And so if you do have this property, then you can estimate variance using the entire X matrix. So it's the same formula I kind of showed you earlier, but with X instead of X1. And that is going to be unbiased. And then we can just replace our confidence intervals with this new version, which uses this new degrees of freedom, which will be less than GX1, and this new estimator, but now we know that's going to be unbiased. So it's going to give us our type 1 error rate that we want. And so we would want to be able to try to maximize gx to increase our power. Now, how do I generate this gx? How do I make x ranked efficient? Well, there's sort of two strategies. There's pure error degrees of freedom that come from you just replicating rows of the design. And so it's pure error in that, well, if I'm doing the same settings, then if I get variation in that response, it can only be due to sigma squared. It can't be due to any other factor in my design. And so that's why we call this pure error. It's a model independent estimator for sigma squared. And then pretty much everything else we call lack of fit degrees of freedom. So this is a model dependent estimator for sigma squared. It's a little bit harder to go into what that is. I don't think it's very important, but the point is that some of these could exist. So we have these two sort of opportunities to generate degrees of freedom for estimating variance. So this is really sort of a multi-objective optimization problem where we're trying to do all these three things at once. We're trying to minimize the design variances, we're trying to make aliasing go to 0, and we're trying to maximize the degrees of freedom of the whole design. And the traditional approach that you'll find in most design textbooks is they'll do this in steps. They'll first focus on identifying designs that minimize design variances, and then they'll collect all those designs and say, okay, which one of these minimize aliasing? Which is definitely like a reasonable strategy when you have multiple objectives. But what that can mean is that by focusing on one objective first, you might over-optimize for that one and sacrifice what you could do for the others. Now, that being said, I'm actually going to take that kind of approach where I do one optimization first, but I'm going to do the opposite approach of what traditional people do. I'm going to make sure, let me find all the designs that have 0 aliasing, and then among those, find the one that minimizes variance. And that's exactly what a foldover design does. So I'm halfway through my presentation. I'm finally talking about foldover designs. So the idea of a foldover design is that you're starting out with what I call a half design that has half the number of runs, hence the name half design. And one thing that you need to require is just that the rank of that matrix is M so that you can estimate all the main effects. The foldover design generated by H just takes that H matrix and then multiplies it by -1. So it's basically just flipping the signs of all the design settings. The only time it doesn't change anything is if you have a center run of all zeros. And I'll bring that up again in just a minute. So this has been known for a long time. A foldover design is guaranteed to have 0 aliasing between the main effects and the second order effects. And that is the main property that everyone knows about when it comes to foldover design. So I'm not claiming I'm the first person to know that at all. The whole point of this talk is actually it does a lot more than just that. The other nice thing about this is that these design variances for the whole foldover design are completely determined by the half design. And this actually is nice in terms of algorithmic design construction because that means that I can actually search for designs using half the number of runs. I don't need to look through all n runs. So there's some nice implications with that. And there's actually a lot of popular response surface designs that employ this foldover technique. One of the most recent ones are definitive screen designs leverage this, and a lot of the Omar's designs from Peter Hoos and his collaborators, a lot of their designs also have a foldover structure, although not necessarily. So I'm kind of giving away the surprise here in the title, but the main part of this talk is that foldover designs not only give you 0 aliasing, but they also are going to give you degrees of freedom for estimating variance. And so let me kind of show you how that works. So the first step is that you can take your half design and you can partition it into capital G plus 1 groups. So the plus 1 is that there's a special case if you have center runs, which I'll show in just a minute. Now, and then all the other groups are going to be comprised of rows that are not equal to center runs, but they're not just replicates of a row. They also include what I call the mirror image of that row. And you'll see in a minute why I group those together. And the point is that if your half design has this structure, then your foldover design is also going to have this group structure, but now you have twice as many rows in those groups. So these two, there's a lot of text on here, but I basically copied and pasted this bottom part with this top part and just put 2 times down here. All right, let me do an example of what I'm talking about. So here are 3 possible half designs, each with 8 runs. So I'm going to be really looking at a design with 16 total runs and 4 factors. So the table down here kind of describes all these different groups. So this N0, this is counting how many center runs. The half designs 1 and 3 don't have any center runs, so those are zeros. But notably, design 1 and design 2, all of their groups either have or just have one unique row inside of it. D3 is in the other extreme, where I have 4 unique groups, no center runs. This has 1 member, this has 2 members, and this bottom one has 3 members. So notice it's replicates, but also it includes mirror images as well. So that's why these are all put together, even though this row is technically different from that one. And the similar here, mirror images of each other. So let me show you at least how pure error degrees of freedom come out of this. So here's my half design up top, and I've got more columns in here, but here are the eight groups, each having a unique member. And then if I do the foldover design, you'll see that in each group is just the foldover of the other run. Now, when I populate this whole foldover design, you'll see that I still don't have any runs that are replicated. I should point out I had to transpose these designs because I can't put them all vertical like that. But you'll see that there aren't any replicated runs in the foldover in the foldover design. So I have 0 pure error degrees of freedom. I might still have lack of fit, but I don't have any pure error degrees of freedom. If I move on to half design 2, which is the exact same design as H1, except I replaced the first row, the first design point, with a center run. Well, this is where the special thing comes up with center runs. Folding over a center run gives you another center run. And so the number of pure error degrees of freedom, this should actually be 1, sorry about that typo, is 2 times the number of center runs I have minus 1, which is just actually going to be 1 pure error degree of freedom. Again, sorry about that typo. Now let's look at H3, which is another extreme case. So I've got this row sort of all by itself. There's 2 in here, 3 in there, and 2 in there. Now, look at what happens when I fold over these groups. When I fold over these 2 pluses, which are replicated rows, I get another pair of replicated rows. So I would get twice as much pure error degrees of freedom as I get from the half design. Something similar happens over here with this other group. All of these first 2 rows, when I fold them over, I get the third row twice. And then if I fold over this last row, I get the first row. This is why I pair replicates and mirror images together in groups. And then we see something similar happening here. So the number of pure error degrees of freedom in this case goes up to 8, which comes from this formula here. So this leads to what I call the foldover theorem, which is really just describing all the things that a foldover design can give you. So let's say that you have a half design with M plus V runs. So the V are the extra runs that give us this property, giving us this group. Then the foldover design has these 4 things. It's guaranteed to have 0 aliasing. That's a well-known property. The degrees of freedom for estimating variance is equal to P plus LX, which has a lower bound of V. It could be bigger than V, but it's a lower bound by V. The pure error degrees of freedom is comprised of these 2 pieces. So this is the center run contribution, the formula I showed earlier. And this is the replicate contribution from what I showed with like the half design 3. And then this is just saying that the lack of fit degrees of freedom is going to be at least whatever's left over and minus this number here. So I'm not the first person to notice this, but I'm the first person to sort of generalize this for any sort of half design. So Brad Jones and Chris Noxheim, they did augmented definitive screen designs where they added runs to a conference matrix, which is usually just M by M, so V is 0. They added 2 more runs to it, and by doing that, they generated degrees of freedom for estimating variance, but it was only going to be lack of fit degrees of freedom because it didn't have any replicated rows. So really what I'm doing is I'm recognizing that that technique they use actually has a lot more ability in terms of estimating variance. There's a lot of different options. So the question is, what's the best foldover design then for stage 1 inference? And so the way that I answer that question is I do this criterion called the average expected margin of error. I basically did this, what I was mentioning the previous time I was on here. I had a paper called Optimal Designs for Two-Stage Inference, which is doing basically the same thing, except now I'm conditioning on foldover designs, which completely eliminates my need to consider aliasing in that equation, and it simplifies then into just these three pieces. So this CGX, this is just some annoying bias constant that comes in with estimating sigma. And then we have our critical value, and then we have the average of the design standard errors. And so this actually has a nice interpretation, although it isn't clear from the formula I gave you. But because this is related to margin of error, a nice interpretation of this, just trust me, is that the value of the average expected margin of error tells you the minimum signal-to-noise ratio you can have to achieve a power of at least 1 minus alpha. So for example, let's say you had a design whose average expected margin of error was 1, and you used alpha of 0.05 to calculate that. That means that you should expect to successfully detect factors with a signal-to-noise ratio of at least 1 with at least 95% probability. So it's actually nice that it has that interpretation once it's kind of explained to you. Um, so actually finding the design, I'll just say that I wrote a construction algorithm. If I have time, I can demo it in R. But basically, it takes as inputs the alpha level you want. Obviously, it takes into account the run size and factors that you need. But you can also specify the minimum number of center runs you want and the minimum number of replicated rows that you want to kind of gauge how much pure error degrees of freedom that you're looking for. Now, this is just a minimum number of center runs and replicates. It is possible that my algorithm will say you need more than that, but it's just a way of making sure that you have like a minimum number to achieve some inference property. You can do a mix of categorical and numeric factors, but I'll just mention that if you specify a numeric factor, one thing that my program does is it requires there are at least one zero level for each of those factors in H. So kind of borrowing what Jones and Nachstein did in their definitive screen design paper. That's just to ensure estimation of quadratic effects. So for the ethylene experiment, coming back to what we did, remember they didn't have any, they didn't want to consider any zero levels. So it's just plus or minus ones. And so here I'm kind of partitioning their whole 20 run design like I showed you earlier. And all of these groups with just two rows, they don't generate any pure error degrees of freedom, but I do get it from here. I get two pure error degrees of freedom from this group because this row is replicated and this row is replicated. So the total number of degrees of freedom for estimating variance is 3, comprised of 2 pure error and 1 lack of fit degree of freedom. Now, if you look at the average design standard errors for this design, it's 0.270, which is going to be greater than this value here, which is if I'd used an orthogonal design. 20 runs is a multiple of 4. So there is a strength 2 orthogonal array here that we could use. And in fact, I'm pretty sure the person I worked with, he told me, hey, I cracked open Doug Montgomery's book and I found this design. And I said, well, why don't you try this other approach? And they were open to that. So it was good. But the average expected margin of error for this design was 0.791. So I should be able to detect with high power an effect size at least that big. So just a quick analysis of what that experiment looked like. They found that these three factors were the only ones that were important, which kind of supports this effect sparsity principle, or really factor sparsity principle. And so that also means when I do my second stage analysis, I only need to consider 3 two-factor interactions between these three factors. And that's sort of summed up in this table here. If it's red, that means it's a model that didn't include those effects. If it's green, it means I did. And so trying to minimize, I won't go into it, but this other criterion that I call modified BIC, this model here that includes the two-way interaction between 1 and 4 was slightly smaller than the one with just main effects. So we ended up deciding that was the best model. And just real quick, this is just what the R squared of that model looks like on the data. And so it fits the data pretty well. And so, yeah, we had 37 possible effects to look at, but I only found that I needed 4 of them. So we could see the effect principles working in this example. I will kind of go quickly through the rest of this because I know we're getting close to time. But one thing I wanted to point out is that there's a diminishing return in terms of how many degrees of freedom that you want. So this is a picture of this part of the margin of error as a function of gx and different values of alpha. And you can see that for most of these lines, after about 3 or 4, it kind of levels off real quick, which means you're not going to get a whole lot of return out of trying to make gx larger and larger. And part of that's because it has a lower bound that you hit pretty quickly. And I was worried about this at first because I'm not recommending that people do foldover designs all the time. And actually, the foldover theorem tells us that's a bad idea. So, for example, let's say I had 40 runs that I could do and 8 factors. Well, then the half design would have 20 runs, which is 8 plus 12. So this is our V. And remember, GX is lower bounded by V. That is way more degrees of freedom than you need to be able to estimate or to be able to get your margin of error to be a small size. So I just want to say, I'm not recommending foldover designs be done all the time, because if I'm making GX this large, that means I'm going to have a downside of being able to estimate my possible second order effects. So there's actually a really simple fix for this. It's an augmented design approach. The idea is what you do with most power analyses. You kind of figure out what sort of signal to noise ratio you want to be able to detect for the main effects. And then you construct your foldover design with the fewest number of runs, so this criterion is less than or equal to that value. And that part of the design, you only use that for doing your stage 1 analysis. Then you augment your design with extra runs, dA, that focus on inference for beta 2. And I'm going to do that using this Bayesian A criterion because it's very fast to do it computationally. And the way we get it to focus on beta 2 is by assigning them large prior variances. And so when I do my stage 2 analysis, then I would use the whole design, both the foldover and the augmented design. And it's worth pointing out that when do you find the augmented designs? You could actually wait until you get the results of your foldover design to find the augmented runs if you want to, or you could do it ahead of time. So just a quick simulation study to show why what I'm doing is maybe better than what you find in most textbooks. Let's say we have 16 runs and 5 factors, and we look at a 2-factor interaction model. This is a classic design of experiments problem. And in fact, if you do a half fraction factorial design, this is the most popular because you can actually estimate all of the parameters, and you can do them with the minimum possible design variance. So it seems like, why wouldn't you do that? Well, the problem is because you can't estimate sigma squared with that design. There are analysis methods that you can use, one of which is the length method, which is a sort of graphical approach that generates sigma squared, an estimate of sigma squared, assuming the effect principles. But it's really easy to figure out cases of where this approach can fail. So we created 3 competitors, 3 foldover designs with 14 runs, and then augmented them with 2 runs to get to the whole 16. And so here are the 3 half designs. It's not particularly important where they came up, but the point is that this middle one here has a lot of pure error degrees of freedom, and it has the smallest average expected margin of error. So it should be at least the most powerful for looking at the main effects. So I simulated 500 responses from different models. I'll describe those in just a minute, varying the number of active effects and active 2-factor interactions. I changed the signal to noise ratio, kind of changing how powerful these effects are, and random signs, whether they're positive or negative. I'm going to analyze my designs using 2-stage analysis. I'll analyze the half fraction using the length method. And I'm going to report the true positive rate and false positive rate across the main effects and the 2-factor interactions. So here are my 6 different scenarios. I've kind of labeled like what issues we expect. For scenarios 1 and 3, these are like classic. They all meet the effect principles, so every analysis should do well. 2 and 4, these kind of suffer from having a small signal to noise ratio, which can affect our ability to detect effects. And scenarios 5 and 6, those violate the effect sparsity principle because more than half of the number of effects that we could have are important. And so here are the true positive and false positive. True positive is up top, false positive is at the bottom. And so here are my 4 different designs. These are the 3 that I showed you. Remember, red is the one that had the smallest average margin of error, and the blue is the traditional fractional factorial design. And so you could see that at least for the main effects, the red line is on top. That's expected. It has the highest average margin or the lowest margin expected. Yeah, the lowest average expected margin of error. And that's true for all of the scenarios. Notably, the fractional factorial design its true positive rate completely collapses in these last two scenarios, and that's because the length method fails in these situations. So I don't know about you, but I don't really want to use a design that has a true positive rate of 0 for some situations. That's just a personal preference, I guess. But the designs I'm recommending, they never suffer from this at all. Um, then if you shift over to the two-factor interactions, you can see that, unsurprisingly, all the methods kind of struggle as you get to these more difficult scenarios. But once again, we see the fractional factorial design totally plummet in some of these situations. So I think the main takeaway from this example, albeit it is slightly a straw man, is maybe we should be gravitating towards recommending these foldover designs instead of just automatically defaulting to these traditional fractional factorial designs. So just a quick summary. I think I've demonstrated that foldover designs are quite a bit more powerful than they were originally thought because they can do this new inference procedure, which was this two-stage analysis, which ensures a lot of desirable properties. And it works, again, even for supersaturated models of having 20 runs and 37 effects. I didn't go into details about it, but I do have a relatively fast construction algorithm that can satisfy certain replication requirements. And I also talked about this augmented design and analysis approach in cases where you wouldn't want to have a whole big foldover design. So that's actually the end of my presentation. Doug, I don't know if you think I have time to do a quick demo of my.
Oh yeah, we
Okay.
got time. Yeah,
All right,
please.
great.
I would love
Okay.
to see this.
Yeah, I think it works. I mean, it's not as pretty as, what you'll find in some design software packages, but let me just real quick get my windows set up. Okay. All right. So shameless plug. This paper was accepted by QREI in their special issue on designed experiments. So my collaborators are Rocky Singh, who was at Binghamton University. I forget where she is right now. Kyle, that was the graduate student that worked on that ethylene example that I talked about, and here's his advisor. So this paper is open access. So if you just search for it, you should be able to download the paper automatically. But the main reason why I brought this up is that if you scroll all the way down to the bottom, maybe there's a better way to do this, I'm not sure, and you go to supporting information, you'll see, well, there should be code here. I don't see, this looks like it's just a PDF. I'll figure that out. There should be code available somewhere on this website. I did submit it for supplementary material, but
Yeah, John, I'm curious because I was one of I'm one of the journal editors,
right.
and Christine Anderson Cook and I were the editors for this special issue, and it looks like something's gone astray if you submitted code.
Yeah. Well, I didn't
Oh,
mean to call you out with that.
no, but it's yeah I just wonder what else we screwed up. I'm sorry
Well,
about that.
that's okay. That's okay. Maybe it might be somewhere else in here that I haven't found, but if you want
Okay.
access to this, you can at least email me and I'll give you access to it. But anyway, so one part of all the code, I have all code to replicate all my simulation studies and all of that, but the big one is this function library that has all of the important functions to run. So you just want to um, make sure you run all of these functions to load them up. And so here's a quick demo of that R1 A05. This R1 means I'm requiring replication of at least one non-center run, and the A05 means I'm using an alpha of 0.05. So first I want to create the 14 run foldover. So I said N of 14, M of 5, and this is me setting all of my possible coordinates, and I'm making everything be between plus or minus 1. So um, this is what it just creates a list of the possible coordinates for each one of those factors. And so this ECI construct function is the way you do this. So you specify the number of runs, and this isn't the runs for the half design, it's the total runs that you want for your foldover. Number of factors, whether or not you want quadratic effects, This is how many initial starting designs that you want. The higher this number is, the more confident you are that the design it gives you is actually a really good one, if not the best. This is how you specify the minimum number of replicates for non-center runs. This is minimum number of replicates for center runs. I set that to 0. And then alpha, and then the core camp. All right, so let's click run on this. All right, so this is actually giving a lot of output, but I like a lot of output to make sure things are running properly. It tells you what design it's working on, and it tells you what the initial value was for the first random generated design, and then it reports what the final value is for the last design it finds. And what you'll notice is that you get the same number over and over again for the final value, which tells you it's finding the same design each time. And part of that's because the half design only has 7 runs and 5 columns. So there's only so many options you can have. But it looks like it's working fairly consistently. If I look at what's coming out of this opt fold, you've got these 4 different things. You've got the best half design, the average expected margin of error value. I call it ECI. That's an artifact from my previous code. And I also store the results of all of the initial designs as well, just in case you wanted to do a bit more exploration. So this actually outputs the half design. So I need to run this foldover function on the best half design so that it actually reports the full design. I need that for the augmentation. So you actually get a lot of output when you run this foldover function. You get the foldover design as the first object. And this DGS and NGS, that's kind of corresponding to that table. It identifies the group structure of your half design. So this is telling me that I've got 5 groups. None of them are center runs. And I'm replicating twice or have mirror images for those last 2 groups. I won't talk about what F, but P is the number of pure error degrees of freedom. L is the number of lack of fit. And G is just adding these 2 numbers together. So this is a design that just has pure error degrees of freedom. This is my full model matrix. This is the main effect model matrix. This is the model matrix for the second order terms. And then this pairs is just the label for each column. So this is just saying that the first column of X2 is the 1-2 interaction between those 2 factors. All right, so all I really want to save from this is the foldover design. So that's what D.0 is. And so if I want to augment with 2 more runs, I use this Bayes A augmentation function, which takes in that initial foldover design. You say how many runs you want to augment it with. Again, whether you want quadratic effects, how many initial designs you want to look at, the core can, and then tau2, this is the prior variance you want to assign to the second order effects. I make it 100. You can make it bigger than that, but that seems to be sufficient. Now, I wrote 1,000 initial designs, and that's because this thing runs super fast because there's only so many runs you're adding to it. So it actually went through 1,000 scenarios in a matter of seconds.
Wow.
So you get, these different, I'll just wrap up. You get these different aspects of the augmented design. And so let me save the augmented piece. And so your final design would be combining these 2 designs together. So there's your full design there. So it's a pretty fast algorithm. It does slow down as you add more runs and add more factors, but it's about as fast as I can make it. I don't know what other shortcuts that someone like Jump uses, but it works pretty well for most scenarios. Okay,
This
that
is
wraps
great.
up my presentation. Sorry it went over a little bit, but
Oh,
I wanted to do that demo.
that's fine. Have you thought about taking that code that we were just looking at, which is kind of remarkable as to what you're doing, and turning that into a jump script?
So I presented this at Fall Technical Conference last year, and Caleb King was there, and he actually wrote something that does this.
Ah,
I don't know if he's worked on that, but he did send it to me in an email, and I got it to work on my version of Jump. So
so
it's
somebody at Jump is thinking about this.
right. Yeah. I also presented this at Jump because they're right down the road from where
Yeah.
I am.
Well,
And kind of told them,
Caleb and Ryan are the 2 guys that would be all over this, I think.
yeah.
And
Yeah,
I
I've
think
talked
this
to both of
is
them.
this is such an interesting idea that I think uh, they should that they should do something with this.
Yeah, they have all the functionality already in their design package.
Yeah.
It's just a matter of putting the pieces together. So,
Well, I'll talk to them. I've got a project going on uh, with Caleb right now. I've got had a funded research project with
mm,
DoD involving 4 universities and medical schools and all kinds of crazy stuff. And we're doing some accelerated life testing on the final product from this research, and I got him involved in doing that because he wrote that routine
mhm,
in Jump,
mhm.
and I figured it would be good to get him involved, and he's really excited about it because the results are looking so. So he and I talk a lot, so
Okay,
I didn't realize that he had done something with it because I think this is a really nice idea.
thank you. Yeah, anyone else I can push them to incorporate it, I'm all for it.
I don't think we have any questions from our uh, audience per se, and John, that's actually fairly common.
Okay.
Uh, 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 Sometimes what happens is most of the people that see this presentation see it offline,
Hmm.
and sometimes we'll get questions that come in, after they've taken a look at it. So don't be surprised if something pops up that I can't answer, and
Okay.
I need to have you get involved in answering that. Uh, this is really interesting work. Um, and let me bounce something off of you, just out of the blue here. Uh, I've had a research project for a number of years, working with another group of people from the Defense Department, uh, where the size of the experimental design uh, is problematic.
Hmm.
Um, we're typically what we're involved in is operational testing. This is something that the DoD is required by congressional mandate to do for new systems that are going to the field. You have to take essentially the final item, the prototypes that are ready to go into production, and you have to take them out into a field environment, and you have to test them under realistic operating conditions to make sure that they actually will do what they're designed to do.
Hmm.
And some problems are uncovered in development testing, but a lot of the things that you might want to really investigate are difficult to study in development testing. So these full scale tests are uh, uh, are important, and they're complicated because they require specialized ranges to do the tests, specialized equipment, uh, and so running one of these operational tests is a very complicated affair. Um, they're not interested in large experiments because of the amount of time it takes. Um, and
Hmm.
the number of factors that they have vary typically between about 5 and 10.
Hmm.
So fractional factorials are the way to go. But something like a foldover experiment, you do the first part, you take a look at what you get, you augment and do more runs.
Hmm.
Not possible in most cases
Hmm.
because the ranges are fully booked. So,
Okay.
so you might do a 16 run design or an 8 run design, and then discover that you need to do another, say, 8 runs, and you go back to the range manager. and you say, well, okay, we need to do 8 more runs, and they say, well, okay, we can schedule you in the summer of 2028.
Uh-huh. Right.
That's the next time we have ranges.
Right. Yep.
Yeah. So what we've been looking at are non-regular designs in the hopes that that you can use the non-regular designs to untangle main effects and interactions
Hmm.
because interactions are fairly common
Hmm.
in these situations. And we've been trying to look at different analysis methods that work for these designs. And I had a PhD student named Carly Metcalf who teaches at RIT now, and she developed a method called alias optimal methods, in which she takes advantage of the alias structure, and she has an algorithm that will sort out the main effects and two-factor interactions for 6 to 8 factor
Hmm.
non-regular designs,
Hmm.
and it works beautifully. We've got a couple of published papers on this, and I've been investigating other methods, and what we've been looking at is generalized regression methods. Things like lasso,
Hmm.
and we've actually found that lasso works really well on some of these non-regular designs, that you can
Hmm.
untangle models that have 4 or 5 main effects and 2 or 3 two-factor interactions fairly easily.
Hmm.
So I kind of wonder if you see an interest in non-regular designs as something that kind of parallels what you're doing here.
Um, well, really what sparked my excitement about this project was a lot of my work with Brad Jones
Yeah,
has been about having designs that are able to give you some assurances in estimating variance.
right.
Because um, that actually, to me, is, I think, the most important thing, or should be like one of the most important things, is to have some assessment of your system's variability. Because all aspects of inference are about um, size relative to noise.
Yeah,
And so if you have very little idea as to what the noise is, um, it just opens up opportunities for you to make the wrong conclusions.
absolutely. Yeah, yeah.
And so the just jumping to the non-regular designs, um, you're still opening yourself up to that possibility unless there's some way of estimating variance. I mean, um, there's a way to have both. Actually, um, one of the designs that I showed, that C3 design in my slides, that actually, I could be wrong, but I'm pretty sure that actually does give an orthogonal main effect plan.
Oh, okay.
So it's probably a non-regular design or something to that effect. So you can generate, these non-regular designs from folding over,
Yeah,
um, right?
yeah,
I mean,
yeah.
it's
There are a number of
resolution
different
three,
algorithms.
resolution four. That's like a
Right,
well-known
right.
property of foldover designs.
A lot of them turn out to be things like projections of Hadamard matrices and things like that.
Right.
But yeah, you're right.
So I mean, I'm all for non-regular fractional factorial designs, but that's why I'm really trying to push practitioners to ask themselves, uh, how important is it for them to guarantee some reliable estimation of sigma squared?
Yeah,
Uh,
that is
and
important.
right, and the beauty of what I've presented today is you don't have to make any um, uh, assumptions if you have the pure error degrees, well, fewer assumptions, um, to be able to assure that at least you get that information out of what you're doing.
Right, and I think that's really important.
Hmm.
But the non-regular designs that we have focused on for the work that we've done have all been orthogonal main effects designs.
Right.
And that I think that's an important piece of the puzzle also.
Right. I mean, I do think that and people have different definitions of non-regular designs. I've always learned them as being they have to be orthogonal main effect plans.
Yeah,
And it's just that their aliasing structure is more complicated than totally confounded or not. Um,
exactly. Plackett-Berman designs being a sort of a simple example of that.
right. I'm
Uh,
not sure what your what the method is you developed with your student, but it's entirely possible that what you developed can be applied in the stage two analysis that I'm doing instead of
ah,
doing my modified BIC approach. But the what I didn't talk about the modified BIC approach, but the main gist of it is you're doing a BIC calculation, but you're assuming that your estimate of variance is the truth.
right.
And it actually gives you better behavior of the BIC criterion. And so that's something that you might think about is how your method might benefit from leveraging a estimate of variance that you're pretty confident about. I know for the lasso, I've done a lot of research with lasso. I actually have a paper on optimal designs for lasso. Um,
Oh,
but a main part of lasso is tuning parameter selection.
yeah.
And having an unbiased estimator for variance is incredibly valuable
It'll
because it
help.
tells you
Yeah,
when you're overfitting.
right.
And so that's just another opportunity for having that variance
Well,
estimator to improve.
let me suggest that you get in touch with Carly
Okay.
at RIT and get her to talk to you a bit about some of the methods that she developed, and there may be something useful there. By
Yeah.
the way, we just have a question that popped up, and I need to read it to you, see if you want to try to answer this. The question says, have you compared your designs to other alternatives, such as fractional factorials with center points? And he said he rarely sees unreplicated factorials.
Hmm. Um, well, I did do my one comparison in a simulation study with a fractional factorial design, but adding center points, um, I haven't I haven't really gone in depth on doing like a full comparison on
Hmm.
that. I guess to me it's like I kind of already see um the benefits of what I'm doing. And
Yeah.
I my algorithm has that opportunity to find a fractional factorial design with center runs if it really thinks that it's important. That's
If it's a good alternative.
right. And
Yeah.
so like yeah, the beauty of that average expected margin of error criterion is that it's a way of combining two objectives without you having to weight one versus the other.
The
It's a
other.
way of balancing design variances with degrees of freedom. So it would be able to tell you, like in this context, like how many center runs to add to it if you wanted to do that, or how many other would it be better to do replication? Because with center
Right.
runs, it does limit your ability to um, do inference on two-factor interactions. So it would be able to balance all of those things. And it would hopefully, if that were an optimal structure, it would be able to find
It
it.
would find it. Yeah. Yeah. Yeah.
And I didn't even also, there's also opportunities for, you know, the design's ability to detect lack of fit, um, for why you might want to add more replication for center runs. There's a lot of exploration on like using this method in this construction algorithm to generate different design classes.
Right. Well, I appreciate your spending some time with us. We're rapidly running out of time here.
Yes, sorry, that I think the
No,
demo
no,
took
no.
up more time
This has been extremely informative. I've learned a lot, and because I remember your paper in our journal, and I just now
than.
need to go back and read it again more thoroughly. By the way, since we are ending up this session in April, this is our last fireside chat for the spring, and so we're going to start back again in the fall, which for us our fall semester starts in August. So we'll probably have August, September, October, and November fireside chats. More information about that will come. I encourage people to look at the past recordings in Coursera. And as always, I look forward to these occasions. And John, I want to thank you again very much for a very informative talk, and good luck with this work going forward, and keep after Caleb.
I'll do what I can. Oh,
I'll
you're
do what
welcome.
I
Thanks for
can as
having me.
well. Thank you.